Hello, welcome to a presentation, Manure Management for Water Quality, Hurdles with Soil Health. My name is Francisco Arriaga. I'm an associate professor and state specialist in the Department of Soil Science and the Division of Extension at the University of Wisconsin-Madison. In Wisconsin, we have significant problems with phosphorus in streams. We have a lot of streams that are impaired by phosphorus. And some of this phosphorus comes from agricultural production. We are a dairy state, and we have a lot of dairy operations. One of the forages that we grow here is corn for silage. Here's a picture of a field after harvest for corn for silage. So you can see there's very little residue left on the soil surface. And often these fields are the ones that are receiving manure because they become available earlier in the fall compared to other fields. So with that becomes an issue that, we're applying manure and we have very little residue. We try the best as we can to incorporate that manure, but we still have some issues where we could be losing phosphorus under these conditions. So we have been doing work looking at cover crops as a way to reduce sediment and phosphorus losses. And so today I'm going to share two different projects looking at things that we've been working on, looking at management to reduce phosphorus losses from silage operations. First one deals with cover crops and tillage. So we're looking at no-till and conventional till with a cover crop and without a cover crop. Here, I'm mainly going to be talking about the treatment where we had a cover crop chemically terminated a couple of weeks before we planted the corn. For the purpose of this project, we use a rainfall simulator that you can see here behind this tractor, the tower. There's an oscillating nozzle on top. And so what we do is that we pound these frames on the ground. Here's a close-up of the frame. They're meter by meter. Pound them in the ground, then we put the tower on top and rain on top of these frames at a rate of 3 inches per hour. And we put this wand here, it's a PVC pipe with a screen on it attached to this hose that has a vacuum to it. And that vacuum pump, it's in the back of this wagon where we also collect water samples and sediment samples for the purpose of analysis. This work, I mentioned we did tillage, no-till, also the conventional, which is a fall chisel followed by a spring finisher operation. And we conducted simulations at 3 different times of the year to get different crops, growth stages, if you will, of the cover crop as well as the corn. So we did simulations in June, October, and April. All of the treatments received 10,000 gallons of liquid dairy manure, which it was injected. Here for some results. So what we're looking at here is runoff by the different simulation dates that I mentioned. And this is runoff in inches. The white bar is no cover crop, and the bars with the lines are cereal rye. As a reference here is the amount of water that we applied, about 3 inches. And overall, if we look at the overall effect of cover crop, it reduced runoff losses by about 50%, perhaps maybe a little bit less. But we see that there's a dependence related to the time of the year. So we can see here in April, where we have a lot of cover crop growth and a lot of biomass, we had the best benefit from that cover crop, where the cover crop reduced erosion and runoff, that is water runoff. However, in October, we see here how that cover crop looks like, very little residue. So we didn't really have an effect from that cover crop. In June, what we're looking at here is the no-till treatment, where we have a lot of the residue on the surface, whereas on the till treatment, there was a lot less residue on the surface, almost very little. But still, we saw a slight benefit from that cover crop. However, it's not significantly different from the no cover control. When we look at, so I guess the point on here is that the amount of biomass on the surface of the soil matters. When we look at the total phosphorus load, and this is grams per hectare, we see that it follows the runoff path, where the only significant differences statistically is in April, where we have a lot of residue. In October, very few, no significant differences. And in June, a little bit of a difference, but not statistically significant. So I guess the story here is that the amount of biomass on the surface matters, something that we know. Interestingly enough, tillage did not come up as a factor that was significantly contributing to reducing runoff or phosphorus losses. However, it seems to be there's an interaction with cover crop use and tillage, especially with the conventional tillage, and that's more related to the June portion that I just talked about. We have done also some soil health measurements, and so I want to share with you a few of them. So here's potential mineralizable carbon, where we're looking at the cover and no cover scenario, and we see that the cover crop increased the amount of potential mineralizable carbon. The Solvita CO2 is sort of similar or analogous to the PMC measurement that I showed you, and so it shows the same effect. So overall, both of these tests show that the cover crop improved the activity of the biology in the soil, microbiology. Looking at potential mineralizable nitrogen down here in the bottom left, we see again the cover crop helped increase the amount of potential mineralizable nitrogen, so some of those organic pools of nitrogen. Looking at physical property, aggregate stability, and here I'm showing the cover crop harvested treatment that we didn't do for the simulations, but I'm showing it here for the purpose of the cover crop. We see that the cover crop was very effective, those roots, in creating aggregates in the soil and creating more stable aggregates compared to not having a cover crop. So there is a benefit, again, from that cover crop. However, again, in this case, tillage was not a major factor, as we found. So one could say that the cover crop improved the soil function, which is at the heart of soil health, is what we're looking at, is function, by increasing the aggregate stability, which in turn improved infiltration. You know, we cannot attribute all the improvement in infiltration to the cover crop, because there's also the effect of the residue on the surface, you know, reducing crusting and other things, but there is some correlation here, it appears. And so that infiltration improvement due to the cover crop reduced phosphorus losses as a whole. And here we're looking at the data aggregated for all three simulations. So this would be like the annual effect, if you will. So what we see here then is that cover crop can be quite effective in improving health properties of the soil and also improving water quality. But is this the case all the time? So what I want to share with you now, the second study I want to share with you, it's related to mainly tillage, and we're looking at different times of the year. Primarily on this study, we're focusing on the winter season, the frozen season. So here in the upper Midwest, we have conditions where the soil freezes. And so for this study, we were looking at two tillages, a fall chisel and a no-till system, and two winter liquid manure applications. So in Wisconsin, farmers can apply manure during the winter months. There's some restrictions related to it, but they can apply manure. So we were looking at what time of the year is time of the year an impact, produces an impact or has an effect on phosphorus losses. If we're going to apply, what kind of best management practices can we follow? Here's an overview of the plots. You can see here. So each block here that you see, there's actually two plots, one on the left, one on the right. You can see the plot line here. They are grouped or paired by tillage. And so you see these white lines, those are PVC pipes that connect to this box here at the bottom. And that is to collect runoff from each side. So this is the left side and the right side, and goes into this box. This is a close-up. Here's one of the plots. We have these wings at the bottom and a collection point. And that PVC pipe goes into the box. This is the inside of the box. And inside of the box, we have these buckets with these flume, these crowns that serve as sample splitters. So what happens is that as this bucket fills up, then we can subsample, take a subsample and go into the next bucket. So that increases our sampling capacity. So this comes from the left plot of the per plots in this scenario, and then this one goes from the right plot. So looking here at two winter seasons, a winter of 2015-2016 and winter of 2016-2017. And in the solid lines, that is the no-till treatment. The colors denote the manure management. Here I'm mainly going to be focusing on the tillage. The dashed line is the conventional till, which it was a chisel in the fall and a spring finisher in the spring. So we have runoff, and what we see overall, if you look at this winter season, was that we had greater runoff in with the no-till. In the second winter season, we see the same pattern, even though we have a little bit more variability. But we see that overall, the no-till, there was greater runoff from those fields. Looking at loading, we see here total phosphorus for the two seasons again, and this is split by tillage. On the left is chisel, on the right is no-till. And we see overall, again, that we had greater phosphorus losses for the no-till scenario, even where we didn't have any manure applied. If we look at the entire season for these two scenarios that I'm talking about, and look at runoff, here we have then the events by, or the runoff events listed here on the x-axis, and we have runoff on the vertical, and we have on the green line is the cumulative no-till runoff, and in the orange is the cumulative for the chisel. And so we see this trend kind of continues for the entire period of time. In the no frozen period of the year, we still have more runoff in the no-till in the first season, or the first year that we looked at. In the second year, we see that that trend still continues, even though the difference is not as large. We also we've been continuing to monitor these plots, this research site for longer periods of time. And we're working still with those data, but we're basically seeing the same type of effect in other years. So overall, no-tillage produced 48% greater runoff compared to the chisel. The no-till runoff was dominant during the non-growing season, the frozen season, whereas in the non-frozen period of time, the chisel had more runoff. But if you look at the whole year, there's more total runoff for a year on an annual basis for no-till system versus the chisel system. Looking at sediments here as total solids, same setup for the slide, we see that the no-till had 59% greater total solids compared to the chisel. But the total solid losses, or the sediment losses, are more dominant during the non-growing season, which makes sense because when the soil is frozen, those particles tend to be stuck together more, right? And they're harder to separate. So why the difference with tillage? So this side, the plots that we have are on a 6% slope. And so what's happening is that the chisel in the fall, it's creating these depressions in the field. So we do it along across the slope, along the contour. And so we attempted to also measure the infiltration capacity of these soils, but as the soil freezes, the water inside the pores freezes, becomes a solid, and so the infiltration capacity goes down regardless. And so what happens is that these depressions in the chisel allow for that water to be in a longer contact time with the soil, so it's giving it a greater chance for that water to infiltrate into the soil. Whereas under no-till, that's more of a smooth surface, so that water is more free to move downslope as that snow melts. And so indeed, that's what we find when we try to track the overall effect. We see that there's greater infiltration because of that depressional storage when we take into account the depressional storage. Another thing interesting that happens is that with the manure application in the winter, it lowers the albedo. So that means that the surface becomes darker. And what that creates is that the snows melt faster too. So this exacerbates this problem if you apply manure in the winter, liquid manure. If you were to apply solid manure, which we didn't do in the study, but other studies before, what the solid manure does, it acts more as a blanket and insulates the snow, and so it slows down the melt of that snow. But in the case of liquid manure, it increases melt. So I guess when we're looking then and trying to look at these things and looking at management practices, so is more infiltration is always better, I guess, comes to my mind. And the case, I guess the answer to that to me, no, it depends, right? So if we have a case with drain tiles, perhaps we don't want a lot of infiltration because it'll reach the tiles and then it'll reach surface water. Shallow soils with fractured bedrock, that could create a pathway where that whatever chemicals or things that are applied on the surface can reach a fracture and reach groundwater relatively easy. So with that in mind, I feel that conservation practices that promote and management practices overall that promote soil health are important. We need to do that, but we need to keep in mind the soil health needs and the water quality needs. So we need to kind of look at what works in one field might not necessarily work in another. So we need to continue and work on linking soil health to water quality. Thank you for your time.